Well, hello and welcome to another DevNation Tech Talk. We're going to be having a lot of fun today. We're going to be talking to Pete. Pete is going to take us through the world of GPUs. So if you know what a GPU is, you play your video games on your computer, that's what you think a GPU is for. Well, it turns out those GPUs actually have a lot more use cases than just playing video games. And I don't mean Bitcoin mining in this case either. We're going to be doing some fun stuff with GPUs and how you enable them within a Kubernetes architecture and an OpenShift system. And I don't want to spend a lot of time telling you about it because we want to let Pete tell you about it. So Pete also, by the way, is having a rainstorm just like I am. So if we both get washed out here, you'll know what happened to us. But
Fingers crossed.
let's go, Pete.
Okay, thanks, Burr. My name is Pete MacKinnon, and thanks for joining this DevNation talk today on GPU enablement for data science on OpenShift. That is me there. That is I. I work in the Red Hat AI Center of Excellence as a principal engineer. I'm a contributor to the NVIDIA GPU Operator and Open Data Hub projects. And over the past 2 years, I've also been heavily involved in the Kubeflow project, which you just learned about with Joanna's talk previously. And also many moons ago, I co-authored a book on Linux. So that's me. Before we start, I'm assuming that people here have attended the other AI ML talks in this recent DevNation series, and that you already have some knowledge of how modern data science is shaping our world today. And I'm also assuming a certain amount of familiarity with OpenShift and Kubernetes in general. So having said that, we're going to do a quick refresher on data science, talk about the AI ML lifecycle from training to inference. And we're also going to look at some of the mathematical constructs that are used in AI and ML. Then we'll take a look at CPUs and GPUs. Also from there, notebooks and machine learning frameworks. Then we'll move on to a comparison of two operators in the OpenShift GPU operator family. And we'll talk about the components of those operators in terms of GPU enablement. And then we'll finish up with the installation of the operator and a quick demo of a TensorFlow notebook. So, data. There's a lot of it, and it's increasing every year exponentially based on various studies and sources. At some point in 2020, there will be around 40 trillion gigabytes of data. That's also 40 zettabytes. 90% of all data has been created in the last 2 years, and it is estimated that internet users collectively generate about 2.5 quintillion bytes of data each day. So lots of data, lots to process. Models in data science are the instructions for computers to learn how to interpret that vast amount of data on our behalf. We want to train the computers to make accurate predictions. Those predictions could be weather forecasts. They could be the location of oil and gas deposits that could be developed. Perhaps it's pattern recognition or image classification. And certainly in our everyday life, people like Netflix and Hulu and the streaming options out there, those recommendation engines, those suggestions that you get are all done with data science and machine learning models. And currently at the moment, data models could help us manage probably the most important healthcare challenge of our lifetime, which is, of course, the COVID-19 outbreak. So that's the refresher on data and models. Let's talk about the AI ML lifecycle. And there's been various depictions of this. I've tried to sort of make it a little simpler. So on the left, we have sort of the activities that involve the data itself. So collection, analysis, transformation, validation, feature extraction and labeling, which Joanna talked about previously. And of course, splitting for testing and training data sets. So that's the data side. In the middle, we have sort of this activity that is around the model development. So a selection of an algorithm or maybe the development of a new algorithm. Hyperparameter tuning, where we are changing the various details around the model, not the data itself in the model, and then validating that model. And then finally, we have data and model that we need in production, brought together out in production doing something useful for us. And typically that's done as a serving activity where the model is running inference on live data. And in that space, we're doing logging and monitoring of the inference to capture that data. And in between, there's sort of a general flow back and forth. I haven't wired these together in a particular sort of loop or any of that sort of depiction. You have to think of it more as sort of this iterative sort of cycle that goes back and forth. Production models can even inform future model development. Okay. So the two speedometer icons you see there are the areas in the life cycle where we are seeking the most amount of performance from the underlying platform and hardware. Okay, so it's in the training development and also certainly in inference and serving. If you think of video streams and processing that video image data, we need a lot of processing compute power to make that go as fast as possible. So that's the general space of AI ML in terms of data science and the life cycle. But to understand a bit more about GPUs, we need to sort of drop into sort of this level of discussion about mathematical constructs that are used to represent the data. And here we talk about scalars, vectors, and tensors. So a scalar, it's a real number, it has magnitude, and that measures something. Maybe it's volume, density, speed, energy, mass, what have you. A vector is a one-dimensional array of scalars, which provides the next layer of abstraction. And in the physical world, that could provide us information about force or velocity or momentum. Beyond that, we have the tensor, which is a higher order algebraic object. That could be a scalar, a vector, a multi-dimensional array, a multilinear map, what have you. Various types of, it can take on various types of forms in terms of representing real world data. So the modern CPU, which is ubiquitous and has been for some time, today's modern CPUs have advanced instruction sets that make them good for general compute, but also they can do a certain amount of the vector algebra. But with the modern GPUs, they are built specifically to perform these complex tensor operations and do so with a high degree of parallelism. Okay. So when we think of these compute primitives, the scalar, the vector, tensor, how do we think about them in terms of the order of magnitude for processing? Okay, so let's say a scalar primitive could be used to do tens of matrix operations per clock cycle in a CPU. And then a vector-based one could be perhaps tens of thousands in a modern CPU or GPU. But in the modern GPU, a tensor-based primitive can be computed in the hundreds of thousands in a single clock cycle. So these next few slides should not be interpreted literally. Please don't send anyone from MIT down to Raleigh to straighten me out. They are meant to conceptualize a relativity between important mathematical constructs that underlie data science and the means and rate by which those constructs can be operated upon. So in this case, we're using Vermeer's The Girl with the Pearl Earring as a visual representation of model accuracy. So let's assume there's a Vermeer machine and it has one clock cycle to render that portrait, and we're ignoring color rendering and shadow. Just how much detail can be provided? So just relying on scalars, we get a representation, but it's kind of blocky. It doesn't look very clear. We recognize the colors, but maybe not the face. With vectors, the image resolves more, but it's still quite pixelated. There's not enough detail. Finally, with tensors, we achieve an image in all its exquisite detail. Again, this is sort of a conceptual representation comparing these different types of primitives. So that's an image-based representation, which actually makes sense when you think of what GPU were originally designed to do. But what about real-world data that we talked about earlier? So with deep learning, with real-world data, if we think of scalar, vector, and tensors again, perhaps with scalars we can represent a single object, an automobile. With a vector, we can represent movement of that automobile. It has dimensions, but it's also traveling in a particular direction. In the tensor world, with that capability, the possibilities are basically endless. If we model cars and traffic using tensors, we can have classification of those automobiles by their type, their movement, which is normal or maybe it's abnormal, that can be monitored, and we can even have systems that can perform traffic management and predict accidents. So, what's out there today? Let's compare a CPU and GPU that is state of the art. On the left hand, we have arguably the most superior data center CPU in the world based on benchmarks, and that's the AMD EPYC 7702. Okay, 64 CPU cores, 128 threads, 2 gigahertz base clock rate, which can be boosted, and its performance generally in the 32-bit floating point benchmark is between 1 to 2 teraflops. On the right-hand side, we have the latest and greatest NVIDIA data center GPU, which is the Ampere A100. It's actually very difficult to compare these directly due to the very different processor architectures that they have. But if we just look at one metric, which is that 32-bit floating point benchmark, we see that the Ampere is almost 20 times faster. Then if we are also talking about purely tensor operation performance, memory bandwidth, and parallel streaming multiprocessors, then the comparisons between the general purpose CPU on the left and the specialized purpose GPU on the right becomes nearly impossible. So, how do we make use of this? How do we leverage this? Well, data scientists are fond of things called notebooks, and there's also machine learning frameworks that can be used directly in notebooks. And in this series, we've probably already talked about the Open Data Hub. This is a feature of the Open Data Hub. We support builds of GPU-enabled TensorFlow as well as other types of frameworks that are ready to be used with the installation of an Open Data Hub instance. So what the data scientists will want to do is select a particular notebook image. In this case, it's a GPU notebook image, which is built against a particular version of the CUDA library. And the CUDA library is provided by NVIDIA. It's the framework interface for applications to actually talk to the GPU itself. And there's several frameworks that leverage CUDA. So TensorFlow is one of them. There's also PyTorch, XGBoost. There's several of these. So in the context of how this is done with Open Data Hub, it has the Jupyter Hub spawner, and there's actually a field by which we request the creation of a notebook pod, and we want to assign a certain number of GPU to that notebook pod. Okay, in this case, it's going to be 1. There's a 1-to-1 ratio between the request and the availability of a GPU. In this case, there's no slicing like you have with a CPU. If there are 3 GPUs available in the notebook pod, request 3, then that pod will be assigned to that node with the GPU. And this is all done in the background with the operator, which we're going to talk about in a bit. So that's the data scientist view. How do I get to a GPU? How do I leverage it? And this is the payoff. So this is a smoke test I use a fair amount when standing up GPU-enabled environments for OpenShift, just to make sure that everything is aligned correctly. And basically it's doing it's not really exercising a model. It's basically taking a tensor and convolving it, running a filter over it. But what we see here is a 380 times speed up over that CPU in this basic test. Advantage goes to the NVIDIA V100 that is being used by that notebook pod. Now, that particular CPU is not necessarily at the level of the AMD one we talked about. This is just giving you an example of the magnitude of the speed up that's possible when you have GPU-enabled notebooks running in OpenShift. So you're all in. You love this. You're a data scientist. You're going to get performance. What about how do we set this up in OpenShift? What's required? Well, with OpenShift 4, as you know by now, the architecture is entirely operator-based. That's the reigning paradigm over how OpenShift 4 is constructed. So as you might expect, the enablement of the GPU is no different in that regard. It turns out there's two possibilities with respect to enabling a GPU today with OpenShift 4. We have the special resource operator, and you should think of that as a community operator that's contributed by our OpenShift performance team here at Red Hat. It's designed to be a reference implementation for other specialized hardware. So the original form of that was for the GPU, but you can imagine it being used for high-speed NIC cards or other types of FPGA type devices. It has a general purpose in that regard. It also provides the code basis for what would become the NVIDIA GPU operator. And this can be deployed from the operator hub. So that's the special resource operator. We get a fair amount of questions about which of these should I deploy. On the right-hand side is the NVIDIA GPU operator. This one is certified and supported on OpenShift by NVIDIA and Red Hat. And that can be deployed from the embedded operator hub or via a Helm chart that's maintained by NVIDIA. So both operators are available to you in terms of a production and support sort of use case. You will almost certainly want to make use of the NVIDIA GPU operator. And there's a high degree of collaboration between Red Hat and NVIDIA on making sure these things work well on OpenShift. Both these operators require node feature discovery, or NFD, and NVIDIA has also developed an enhanced labeling feature operator. So it can extract even more detail about the presence of an NVIDIA device. It can also put down a label for the actual model, the compute capability, those types of things. So the operator components, what are they? And in this case, we're going to look at the NVIDIA GPU operator. So the first component is the container runtime toolkit. Okay, so NVIDIA GPU operator supports both Docker and Cryo container runtimes. So there's configuration that must be set to basically inform the operator which of these two is the target runtime. In the case of OpenShift 4, obviously it's going to be Cryo. So that's deployed as a daemon set, and it ensures the correct runtime setup for the GPU hook. Then there's the driver itself, and that's a container that's deployed also as a daemon set, and that holds all the user space and kernel space software to make the GPU device actually work, the device driver. So there's the device plugin, that's a daemon set as well, and that monitors the health and availability of the GPU on the node, and obviously that is vital for correct scheduling by Kubernetes. And then finally, there's DCGM, Data Center GPU Monitoring, and that is a node exporter that captures some of the GPU metrics and provides those for Prometheus. Now, I talked about the node feature discovery in the previous slide. What that labeled there with the PCI 10DE present value set to true, that is basically the label that NFD will put down so that the GPU operator can correctly be assigned to an appropriate GPU-enabled hardware node. So the installation is actually pretty easy, and it starts with the embedded operator hub, and then you create what's called a cluster policy. And now, Burr, I'm actually going to do this as part of a demo. So let's switch over here. And in this cluster, we have a project. It's called GPU Operator Resources. Currently, it actually needs to be that name for the NVIDIA GPU Operator install. We'll go to the Embedded Operator Hub. Click on AI Machine Learning and track down. There's the tile we're looking for. The NVIDIA GPU Operator, that's the latest version available, and we'll hit install. And we'll put in that specific namespace. And you see what it's doing there. It actually has a dependency through its CSV on node feature discovery. So it ensures that that is in place. And again, we need that for the correct labeling of the GPU node that I've provisioned for this cluster. And it's almost done. Go back to installed operators. Succeeded. Yeah, we're good to go. We're going to kick that off. And we've created, based on the node feature discovery, a CRD and for NFD, and it's basically setting out daemon sets and pods to go to each of the nodes and collect not just information about whether there's an NVIDIA device there, but also other types of information such as the instance type, if this is in the public cloud, the version of RCOS that's installed, various details that can be put down as labels on the node.
So how many worker nodes do you have right now? And then how many worker nodes have a GPU?
So we have currently in this one 3, and I believe this guy. And I'm just going to increase focus. Hopefully that's okay, Burr, but I want to call out the label that has been already set down by that operator. So go back over here, create an instance. I'll set that back so we can read it. So NVIDIA called their custom resource a cluster policy, but we see the API version, and we see that all the different versions of the images, the various containers that I talked about are UBI8. In the case of the driver, it needs to be aligned with the underlying version of the kernel and OS. So they maintain versions for RCOS, and I think we're going to have upcoming support for RHEL 8 and RHEL 7 very soon. But Burr, you like baking shows, right?
Yeah.
It takes a while to roll out. So let's go over this other cluster and see what's in the oven here. And we have an operator installed. Whoop. There we go. Cluster policy. And because it takes time, that's why we did the baking show. So we see that in this namespace, we have the GPU operator, and we have the NFD master and workers for the daemon sets. The toolkit, DCGM, the driver's all been installed and running. This looks great to me. We're ready to do some serious damage with this. So as a data scientist, I'm going to go over here to a notebook that's running on this cluster where we have a GPU enabled. And this is, I mentioned it earlier, this is kind of a smoke test I use. With TensorFlow and the other frameworks, you can basically specify explicitly what type of device you want to use. By default, it's going to try and use a GPU if there's one available, assuming, all other things are equal. But in this case, this is not really trying to, figure out a model or come up with a probability or anything. We're just sort of exercising the framework, and we're seeing how this operates in terms of the time spent for the CPU and the time spent for the GPU doing the same thing. So let's hit run on that. And probably about 20 seconds or so, 22 seconds, I'm going to say.
And this pod is already scheduled to a worker node that has both CPU and GPU resources?
Correct. Correct.
And I guess so
that's,
on that worker node?
yeah. So on that worker node, obviously it can take advantage of the CPU there. But since we've installed the GPU operator and that node is hardware enabled with a GPU, this piece of TensorFlow code can basically go through and exercise both paths, if that makes sense.
Yeah, make that fun. I think people need to see those numbers right there because they're pretty incredible.
Yeah. And this is with a V100 16 gig. If once we have the Ampere more generally available, you're going to see numbers that are pretty eye-popping. Again, what it means is, in terms of the efficiency and performance for developing models and running inference against those models, this is the payoff with GPUs. Now, CPU, there's ongoing development. Intel has MKL, and there's the various instruction set extensions that have been developed. But pound for pound, the GPU in these types of problems is going to outperform a single CPU. CPU work can be distributed for data science, for machine learning, but these days that's true for GPU, and projects like Kubeflow have operators that can leverage multiple GPUs across nodes. And
Question, Pete, and I'll throw it at you now. It's from Alexi, and it came up a moment ago, but I thought I'd hold it till about the right moment. And he's bringing up a great point. This is great for NVIDIA, but what about my AMD GPUs? So can you talk more about, what does it take to kind of get a GPU ready, one from NVIDIA versus one from AMD, and what are we waiting on from an AMD standpoint?
I can't really, that's sort of a question more for the team that does the enablement at Red Hat. There's been a big head start with NVIDIA, and some of that has to do with just the relationship between the two companies. And there's a fair amount of ubiquity out there in terms of NVIDIA devices and also CUDA and frameworks that make use of CUDA. So it's sort of a groundswell. Now, I totally get the question, and it'll be interesting to see over time what the enablement team will be doing with respect to doing GPU operator deployments with drivers for AMD devices. But that's TBD, I think, Per.
Okay, because it is interesting when you go to this space. I am normally living in the JavaScript, Java, or even Python worlds, but when you get into this world, you got to make sure you have the right libraries also installed because you need the right drivers, those C-level drivers for those devices. So in other words, you can't just basically say, oh, I want to GPU enable my code right now without having the right drivers installed and the right modules installed sometimes in your Python-based app or your Java-based app, because that's actually C code over there on the driver side.
Yep. There is the layers that I talked about with respect to CUDA and then the framework. So over the past few years, there's been times where you need to be careful about aligning that entire stack to make sure everything runs successfully. These days with the GPU operator, it's much more seamless. And part of the deployment of the GPU operator, and again, this is Zvonko Kaiser and his performance team at Red Hat who has developed all this. But one of the things it does is those pods go into running state, but they're also validated. So there's two things that are validated, that the device plugin is working correctly and also that the driver itself is working correctly. So there's sort of two steps of validation. Once those are in place, I, as an engineer, have a high degree of confidence I can launch a notebook pod just like this one, and it's going to work just the way it should. Now, with Open Data Hub, we do curation. They are curated builds with specific CUDA versions of the TensorFlow notebooks. So there is a certain amount of care at the community project level to make sure that it's not entirely random. You as a data scientist shouldn't have to worry about, gosh, does this thing even line up correctly? Does it work correctly? That is the responsibility of communities like Kubeflow and certainly with the Open Data Hub to reduce those barriers, reduce those points of friction.
A follow-on question to what we were talking about earlier: does it make sense to create a cluster with the nodes, with nodes that have the different GPU classes? In other words, different classes of GPU and different nodes. Does that make sense? And the example being Tesla versus, let's say, a normal gamer card, normal gamer graphical card. Would that make sense to have different classes of GPUs and different worker nodes?
So there's a couple aspects to that question. The NVIDIA end user license agreement is kind of restrictive about so-called gamer cards, like the GeForce cards, being used in data centers. So they definitely, from a product standpoint, have the concept of data center GPUs like the V100 series, P100, A100. So that's sort of baked into the end user license agreement. The other part of the question, whether you can have a heterogeneous mix, from where I sit, that's absolutely valid. You might skew your overall distributed training unnecessarily if you have very low end GPU cards mixed with, say, V100s or A100s. But it's the subject of some debate in our team. I think there's people from a benchmark viewpoint would prefer to see it be homogeneous, the same cards, the same configuration, same NIC, all that sort of laid out, homogeneously.
Well, how would the scheduler work in that case, right? So how would it know that this worker node has the low-end GPU, that worker node has the high-end GPU? How would the scheduler handle that?
So in that case, you would make use probably of the NVIDIA GPU feature operator. And with those labels, you would fine-tune your notebook pod spec or whatever framework pod you're trying to deploy out there to basically have affinity to particular types of machines in the cluster, if that makes sense.
Yeah. Using labels, right?
Yes.
Okay.
Yep.
Well, very good. And did you have more to show us, by the way? I interrupted you there with these questions, but they were interesting from Lexi here on our channel.
No, we covered, sorry I went all baking show on you in the interest of time, but it can take some time for, I suppose we could go over and look and just see. Oh, I didn't even.
Well, in that original cluster, like you had 3 worker nodes, which is the standard from an OpenShift install, but one of them was tied to a instance type with a GPU on board. Is that how it was set up?
Yes.
Because I'm assuming the master node and the other worker nodes were regular regular CPU machines.
Right. So actually, this is a mixed cluster. There's only one node with a GPU in it. So in this case, we're running in AWS. This is a mix of worker nodes with different instance types. So now the beauty with OpenShift 4 is with the notion of machine sets, it's very elastic. We can sort of scale up and down nodes. We can sort of, going back to this discussion of sort of the mix, if you will, for the cluster, it's very easy to add in new replicas of GPUs. Now,
And-
Burr, you and I talked about this. There's the cost component. GPUs
Right.
are expensive to buy and they're expensive to run in the public cloud. So there's sort of a economic, you know, sort of thought to this, in terms of how long you run a cluster, or how, when do you actually need that type of capability. So.
Yeah, and so another question related to the same topic from earlier. So if I have several nodes, will it mean that I can create a model that can consume consolidated memory for that calculation, or am I kind of limited to only the memory of a single node?
The memory of a single node, because this is Kubernetes, the computations are happening there on the
Right.
node itself. So now with the distributed training, I should say, operators, say with Kubeflow, you can do things like MPI. There's an MPI operator where you can basically linearly scale up your GPUs and dramatically increase your overall performance.
Yeah, so basically the framework itself would have to have the ability to distribute the model and its associated workloads to those various worker nodes, which have the GPU and their own memory at that point.
Right.
But you would be bound to the memory of a single node unless the framework itself supported something beyond that.
Yep. And
Okay.
such is the case with GPU devices. They are local to that node. So a pod running there is unable to see GPU devices elsewhere in the cluster as it stands today. Now with the Ampere, they've introduced MultiInstance GPU. We're still learning more about that capability. That is more of a static configuration of different, we call them t-shirt sizes, so that you can have a physical GPU and basically slice it up. And that way, you have more flexibility in the cluster about whether, time of day sort of stuff. Maybe training goes on this portion of the GPU during a certain number of hours, and we do inference on these other segments of the GPU in another time of day. So that sort of capability.
Okay. Now, there's one other thing that we are out of time, but I'm enjoying our conversation, by the way. That has come up before with the GPU and the scheduler from an OpenShift Kubernetes standpoint. Essentially, one pod gets mapped to use that GPU, and if that pod is active at that point in time, that is all you get, right? That's one of the things I've heard is a limitation of this architecture. Essentially, one pod can control that whole GPU, and no other pod can be scheduled there. What do you have more to say on that, or what am I saying it incorrectly?
Not well. I'll just qualify it a little bit. On a node, you can have multiple GPU devices installed up to the limit that that particular rack or server can hold. So we have the COE has a server that can hold 4 V100s.
Oh, wow.
And in an NVLink configuration. So in theory, if that's an all-in-one on OpenShift 3 for a variety of reasons. But if that was a node in OpenShift 4, then you could have pods that ask for 2 of those, 1 of those, all 4. So it really comes down to, and that's what the device plugin is doing. Device plugin is basically supervising the availability of the physical GPUs on that machine, of which there might be multiples. So you may have a notebook workload come along that asks for 4. If 4 are available, it's given to it, but that pod is still bound by that machine where there's 4 distinct physical GPUs, if that makes sense.
Yep. Okay. Well, we are out of time. I thank you so much, Pete. It was very enlightening, and I had not really spent a lot of time thinking about the GPUs other than knowing that whenever we do our AI/ML demonstrations, I have personally seen, if it runs on CPUs, it takes 2 seconds to run the transaction. Running on a GPU, it feels like it's 2 microseconds to run the transaction or 2 milliseconds to run the transaction. And it's a notable speed improvement when you can get mapped to a GPU for running an inference or training, right? So it works on both sides, training or inference side. Well,
Absolutely.
thank you so much for that, Pete. It has been
Thank
absolutely.
you.
And then if everybody, I also put Pete's Twitter handle out in the chat, so you can reach out to him from Twitter. You can always, everyone here has my email address, so you can get back in touch with me if you need me. But at this point, we're going to sign off and get out of here. Thank you so much.